Okay, let's do more examples of acid-base reactions in equilibrium. So now we talked before about hydrochloric acid and say in water, and now we know this arrow is fully product favor because we know that pKa of hydrochloric acid is -7, meaning that the Ka of this equilibrium, writing all the dots, the equilibrium constant is really big, and so this is completely dissociated. Also, now we're going to be using another constant. Say that in our chart of pKa, we find that the pKa of hydronium is -1.7. So another thing that is important to learn is about the pKa's is that we can use the values here of the acid here and the conjugate acid here to predict where is the equilibrium favored. And in this case, we notice by the values that hydrochloric acid is much stronger than hydronium. Or in other words, this is weaker. So of the pair, this is the weaker acid. Always the equilibrium will favor the weaker acid and weaker base. So this is another thing that we can say that will help us. So this value already, but when we have reactions that are more complex, other reactions, then we can predict the position of the equilibrium by comparing those values. So here's the pKa's in the equilibrium, then will favor the weaker acid, always. And we're going to apply that into another example. Say that I have now ammonia. And I always like to draw my lone pairs. And now, because I'm going to use that. Now notice that, I'm going to rewrite this water in a little different way. So to show explicitly bonds. So notice this bond is very polarized. As we said before, say that this is delta positive, that's delta negative, delta positive. This is electron-rich spot. So right here, remember our Bronsted-Lowry concept. This is electron-rich, and this species is going to get this proton. So right here in this reaction, water is acting as a proton donor. Therefore, it is the acid proton donor. Ammonia is electron-rich and is accepting this proton. So as proton acceptor, this is the base in the Bronsted-Lowry concept. And again, remember that always the arrows show the flow of electrons. And they always will go to something that's delta negative or negative to the delta positive, like that. So electron rich to electron poor. And we know it's electron poor because of these dipole. Now let's see where the equilibrium goes here. In principle, I'm going to write the double line. So this accepted the proton now became the ammonium ion and water. So that is not conjugate acid. And this became hydroxide, formal charge. So that's my conjugate base. To see where the equilibrium is going, we're going to go to the pKa's of the acids. And so I'm going to go to the chart, but I know those values already. So the pKa of the conjugate acid here, the of ammonia, this is as acid. See that is about 9, right? Now the pKa of water as acid is about 15 as acid. And here I want you to notice that when you see your tables of pKa, there's two things. Notice there is a big difference between this species and that. So here I'm saying hydronium as an acid, the pKa is -1.7. Here, water as acid, the pKa is 15. So notice it's two different acids, hydronium and water. So now in this equilibrium, what I want to do to predict whether it is product favor or reactant favor, I want to look at the pKa's of the acids. And here I see, okay, ammonia, conjugate acid, this pKa is 9. Now this pKa is 15. So what this has always said, that the weaker acid, the equilibrium favors the weaker acid. Of these two, the larger the pKa, the weaker the acid. So this reaction is reactant favored because this number is smaller. So this is a weaker acid. And this concept is relative, so it's weaker. Water is weaker acid than ammonia, but it's much weaker acid, say for example, than hydronium. It makes sense? So it is relative. And I am comparing here conjugate acid here with this acid. So we're going to be doing more equilibriums in another video.